organizers ask us to sign up for the dinner on Wednesday, and we should sign up tomorrow morning, either at the desk where we signed up for the conference or in 208. So please sign up for the dinner on Wednesday, tomorrow morning. And now it's my pleasure to introduce Jim Kelliher from the University of California. He will talk about vortex patches.
Thanks, Emil. So I'm going to talk today about work in progress with Untitled about vortex patches. And let me first display the Euler equations. I know we're all familiar with these, so I'm not going to dwell on them, but let's fix some notation. Use the velocity field, omega is the vorticity associated with it, k is the BO sub r kernel, and g is the fundamental solution to the Laplacian. The BO sub r kernel then being grad perp of g, and that's a notation I'm going to be using throughout. These are equations in the whole plane. So what is a vortex patch? Well, basically, a classical vortex patch, anyway, is an initial vorticity, which is a characteristic function of a bounded domain. And so we let the vorticity evolve in time. And since it's in L1 intersect L infinity, that vorticity, it is in Udovich's class, and so at least you get well-posedness of the solution for free, and U is automatically at least log Lipschitz. We'll find out it's a little better than that in a minute. So there's an associated flow map, which is a unique flow map, which we'll call eta. Okay? And so the vortex patch itself is the patch as it evolves over time. And so omega at time t, omega sub t, is just the flow map applied to omega at time 0. Okay, it's all fairly standard at this point. So there's a result from 1993 about persistence of regularity of the boundary. And basically what this is saying is if the boundary of the vortex patch starts off C1 alpha, then it remains C1 alpha for all time. And this answered a question that had been open and was of great interest at the time. Now, this is the proof that Chemin gives. The theorem that Chemin gives is a little more general, and this is a corollary of it. And I'm going to talk today about Serfati's work. And Serfati's approach is actually, in some ways, you can see both proofs in it, but it is intellectually closer to Chemin's kind of approach. But the one point where we'll see where it touches a little closer on the approach of Bertozzi and Constantine. All right, so where do vortex patches fit in? Well, I mean, they fit in a lot of different ways, but in terms of just well-posedness results, you see that back in the 30s, it was known that you get strong solutions if the initial data is in C1 alpha. And the vortex patches don't really quite satisfy that. But if you drop down just a little bit, you're going to get to the point where, well, the vorticity is in L infinity, but the gradient isn't in L infinity, which would be the Udovich result from 1963. And those two are, in some sense, very close to each other. Of course, they're miles apart. And in some sense, the vortex patch is in between, because the velocity field, as it turns out, is Lipschitz, not just log Lipschitz. And it ends up making a big difference. Okay? But there's a sort of where they fit in terms of the well-posedness theory. And the reason I want to display this is that the techniques that are used to show persistence of C1 alpha solutions, that is the bottom line there, are much different than the techniques that are used to work with bounded vorticity solutions. Basically, in bounded vorticity solutions, you're using the smooth solutions to prove existence. Okay, uniqueness is another story. And the kind of techniques used for the vortex patches, in some sense, are kind of in between. And those kinds of techniques could be used to recover the C1 alpha result from the L1 intersect L infinity result. But, of course, then you would have done nothing but gone back in a vicious circle. Okay? So I'm just, in terms of the smells of the approach, techniques to me, they're sort of in between the two as well. Not just the result, but the approach. That's just a philosophical point of my own. All right, so why talk about Serfati? There were two proofs in 1993, and Serfati published a proof in 1994. Right, it's a 4-page, maybe it's 5 pages. I think it's just 4 pages long. It's very terse, very hard to understand. Right, so why bother to deal with it? Well, the generality of his result is almost the same as that of Chemin's, not quite actually. But the proof uses no paradifferential calculus, which is in some ways of benefit. Of course, Bertozzi and Constantine's didn't as well. Also produces a little more information about the gradient of U when you stay away from the singularity of the vorticity, which is kind of interesting. And perhaps most importantly, I think that it extends in ways much more easily than Chemin's approach does, because of the lack of the use of the paradifferential calculus. So for instance, it's very simple to extend it to a bounded domain as long as you stay away from the boundary. And I'll talk about these last 3 points toward the end of my talk in more detail. And you can apply it to situations such as a vortex patch in a vortex-wave system, which has, I think, some interesting open questions involved in it. And also, if you want to deal with these just L infinity solutions, the second line there, which Serfati studied in 1995, where the vorticity doesn't decay, then it's more adaptable to dealing with vortex patches in that generalized vortex patches in that setting. A vortex patch, I should point out, classical vortex patch vorticity decays in infinity. So the Biot-Savart law applies. Okay? But in the more generalized setting, then it doesn't. And you'd like to ask the question, can you get the same regularity Serfati got or Chemin got, but do it without having vorticity decaying at infinity? Anyway, that's the reason I think it's worth talking about it. All right, so I want to speak a little bit about Chemin's result first. And to do that, I want to give maybe a little bit of motivation for his result and then make a definition or two before I can even state his result, okay, his more general result. So I don't know what Chemin was really thinking. I don't know what his motivation was. But this is one way to sort of motivate, perhaps, his result. So you know that you can recover the gradient of U as a Riesz transform of the vorticity. Okay? And if the vorticity were in C alpha, then in fact the gradient of U would be in C alpha, but certainly in any case in L infinity. But if it's only in L infinity, then, well, the gradient of U would be in BMO, but it wouldn't be in L infinity. And all of the estimates that are going to be involved in this thing in the vortex patch, no matter what method you use, require that you get an L infinity bound on the velocity. Okay? All right, so fine, but the Riesz transform comes so darn close. But it turns out with vortex patch data, just the initial data, so a bounded domain with C1 plus alpha boundary, that the velocity is in L infinity. And so the question becomes, well, the question was, well, as time progresses, do you remain that way? All right, so to generalize the question, you kind of want to say, well, what kinds of discontinuities are there, okay, across perhaps sufficiently smooth curves? How can they be described? And can the regularity of those curves be propagated in time? Well, that's a very vague and open question. Okay, so how can you possibly specify such a thing? And that's really what Chemin did. Okay, so to describe what Chemin did, I first have to talk a little bit about a push forward of a vector field. And this is a concept that's really shared by all three proofs. The idea is if you've got a vector field at time 0, and this is really just from differential geometry, gradient of eta is Jacobian, really a Jacobian transpose of the Jacobian of the flow map transpose. So there's really just a push forward of the vector field by the diffeomorphism. Okay? And so the middle line is just writing it at time t. So right here, that's a push forward operator. And it turns out if you do a calculation, at this point formal, but for smooth data it's precise, that the divergence of the vector field will be propagated, will be transported by the velocity field, as well as the divergence of the vorticity times the vector field. It would seem, was that me? It would seem, anyway, that these, that if you want to measure the discontinuities that might, I'm trying to say here, that the divergence of the vorticity times the vector field ought to come in. If you can get a vector field that cancels out the discontinuity in the vorticities in such a way that the divergence of omega y remains sufficiently smooth, then that should be the key to specifying the kind of initial data you have some hope of them propagating the continuity of, the smoothness of in time. Okay? All right, so Chemin defines these, a set of admissible vector fields for defining this kind of initial data. And so, first of all, the first condition there with this I of x, it says you have a family of vector fields, could be infinite, could be finite, and they're a sufficient family in the sense that at any point, at least one of them is bigger than 0. And not only that, bounded strictly away from 0, bounded over the whole family. All right? And then it defines the space, which at first looks very crazy and intimidating, but turns out not to be so bad. So C alpha of x has really just, it says, one form of it is to say the gradient of f dot x is in C alpha minus 1. Now, C alpha minus 1 is a negative exponent Hölder space. I'll talk about that in a minute. Okay? But notice the gradient f dot x lambda is the divergence of f x lambda minus f divergence of x. And it's the divergence of x and the divergence of fx that we know has some chance of being propagated over time from the previous simple push forward of a vector field, which is why this C alpha space makes some sense. So the idea is, if you start in this space, can you remain in this space over all time? And then the norm there is defined in a way where you just include all the different components that go into C alpha, the regularity of the vector field and its divergence, and the regularity of gradient f dot x. I switched from f to omega there because what we're going to use for f is omega, the vorticity. Okay? So this is a kind of crazy-looking thing. I'm not going to go into this too much detail because I'm going to look at Serfati's definition for the initial data. But it comes, I mean, it's really just a simplification of this statement here, slight simplification of these spaces. All right, so negative index Hölder space, you're in C alpha minus 1 if alpha is between 0 and 1. Okay? And remember, I fixed alpha strictly between 0 and 1 for the whole talk. So it's essentially the space of all functions that are derivatives or sums of derivatives of things that are in C alpha. And that's a more precise definition. It turns out that C alpha is equivalent to a certain Besov space, which is something that Chemin makes a good bit of use of, okay, in his approach, but we aren't really going to ever use that fact. I should also say that Serfati avoids negative index Hölder spaces, and that's because of a simple fact I'll point out in a minute, right? And it avoids some technical complications. All right, so Chemin's result. Well, what it says basically is you have these admissible vector fields, and if to boot the gradient of u naught is an LP for some p strictly between 1 and infinity, of course divergence free, then u will remain Lipschitz for all time. The gradient of u remains an LP. That's no big surprise, actually. That comes along basically for free. The vector field at time t remains admissible, which means basically the divergence of it remains good. Remains in C alpha minus 1, and it itself remains in C alpha. Well, that's what the next line is saying. And the vorticity remains smooth in the sense it's in C alpha of xt. So it's smooth modulo these vector fields. Okay? So how to interpret a result, it's a little bit hard to actually as well. I'll talk about that in a minute. Okay? All right, and then it turns out that the Chemin's, that the smoothness of the boundary of the propagation of the boundary of regularity of a vortex patch is a corollary. And we'll see why that is in a minute. All right, so let's talk about Serfati and Serfati's assumptions in light of having seen Chemin's. So Serfati makes the assumptions at the top there, and we streamline this a little bit by making the assumptions on the bottom. So let's really focus on the assumptions on the bottom. The assumption is that there's some closed set sigma, and outside of that sigma, the initial vorticity is C alpha. Other than that, it's a Udovich velocity, so it's an L1 intersect L infinity. This initial vector field, so initial vector field exists. That's C alpha, and on the closed set, and a little bit distance away from it, it's bounded from below, which is related to Chemin's admissible condition, but there's only one vector field, so in some sense the conclusion is weaker because there's only one vector field. And that final condition holds. Well, it turns out the two highlighted conditions are equivalent. Okay? The top says the Biot-Savart kernel applied to the divergence is in C alpha. And so Serfati avoids the C alpha minus 1 spaces because he always convolves with the Biot-Savart kernel. The bottom condition is actually in some ways easier to use, which says the divergence is in C alpha minus 1. Okay? And so this is kind of like very close to having Chemin's condition with only one vector field. Okay? And hence you can't conclude quite as much. All right, so what does he prove? So assume those three lines are just a copy of what I had from the previous page. The conclusion is the gradient of u remains bounded for all time with exponential growth. And the C alpha norm of the velocity field has double exponential growth but stays in C alpha. And not only that, but there exists some smooth, C alpha matrix, so that when you take the gradient of u and you subtract off the vorticity multiplied by that C alpha matrix, you get something that's in C alpha for all time. which is sort of a nice little conclusion. All right. Yes, Nick. I cannot hear you.
Sorry, could I use a bolus to get you to remind us one more time of the relationship between why not and you is?
Between why not and you, there is no relationship between why not and you. Okay, why not is something, when we see an example, then the next one you'll get a better idea. So on this page, I'll say why Serfati implies a vortex patch result. And this statement would hold for Chemin as well. So in this case, and this is smells more like the Bertozzi-Constantine kind of argument, okay? So you choose a phi naught so that the boundary of the C1 alpha domain is a level set of phi naught. And then you set why not be equal to grad perpa phi naught. Now that's the thing that describes the discontinuity normally across the boundary, okay, of the vorticity. And so these why not, is a generalization of this idea, okay? So in that case, the long and the short of what I've written here is that over time, y will remain tangent to the boundary. And since you showed, since Serfati is concluding that y is in C alpha, C1 plus alpha rather, the boundary is in C1 plus alpha. That's sort of the long and the short of it. Now, with the more general conditions, you can still get the smoothness of y over time, but it's not necessarily that easy to conclude what it means in terms of the regularity of some underlying structure. Okay? I'll talk a little bit about that toward the end. Okay? Well, actually, not toward the end, very, very shortly. Actually, maybe even the next slide. Yes. All right. So what's some other initial data satisfying Serfati's condition? So suppose you have, and this is true of Chemin's, this work with Chemin's conditions as well. Suppose you have a vortex patch, but instead of being a characteristic function, say it's a C alpha function, but it's constant on the boundary. Then the exact same construction gives the exact same result. Okay? And so that's a modest generalization. Now, if you have a C alpha function instead of a characteristic, so the C alpha function is supported on a bounded domain with C1 alpha boundary, and you have a C alpha function, you can apply Serfati as a result, and you'll get a y that remains in C1 alpha. But what you can't do easily anyway is tie that back to the smoothness of the boundary. Okay, so Serfati's or Chemin result applies, but what do you really conclude from it is the question. Okay. All right, so you take a vortex patch, add a C alpha vector field, same thing, that's Serfati initial data, or sums of these things, right? And in the sums, as long as the closed sets are disjoint, and in the sums, if each of those allows you to, like the vortex patch data or item 1 here, allows you to conclude you have smoothness of a boundary, then you would for the sum as well. Okay? So these are just examples. There are a few other examples we have as well. Right? Why is that happening? Okay. All right, so let's give you sort of an overview of Serfati's proof. Stand away from that one. Oh, I have something metal in my... Oops. Okay. All right, good. All right, try not to touch it. All right, so to give an overview of Serfati's proof, the proof... Can you hear me now? Oh, good. Okay. Hands off. Hands off. I'm afraid I'm just going to hit. All right, so there's really an approximation by sequence of smooth vector fields. I'm not going to talk about that. It messes up everything. So everything really in the argument is perfectly smooth. In the end, there's going to be a convergence argument, okay, which we'll ignore. So in all 3 of the proofs have a little bit of a similar smell in that you're bounding the gradient of u and y, which would be grad perpa phi for Bertozzi and Constantine, and the divergence of omega y, I forgot a parentheses right there, in terms of an integral in time of the gradient of u, and it's a nasty-looking inequality, but it's set up for Gronwalds. You apply Gronwalds, and everything works. Okay, I mean, that's the basic idea, right? So, of course, that's simplifying too much, but we've all seen these kinds of proofs a lot of times. So all I want to do is talk about some of the key points in the proof that make it stand out. Okay, so the key points are that it almost all comes down to employing estimates on the Biot-Savart kernel and the gradient of the Biot-Savart kernel. Okay? I mean, of course, there's a lot to glue that together, but all the things that are key come down to that kind of thing. And that's why it's nice, because it's easier to generalize it into other settings. At one point, employs this it really seems like a miracle linear algebra lemma, which probably, hopefully someone here knows the origin of, but it was a mystery to us, and pulls off some crazy-looking estimate. And finally, he doesn't use any paradifferential calculus, but it really does show up in the convergence argument in a little bit, which he suppresses. So that might be an issue for further work. All right, so how do you deal with the gradient of u? So everything's smooth here, so we have a formula for the gradient of u. Okay, a standard thing right there. So what you do is let v of t be the expression toward the bottom there, where v of t then is slightly bigger, well, is bigger anyway than the gradient of u, and we want to estimate v of t. Well, how do you estimate v of t? Well, the first term's easy, because L infinity norm of the vorticity remains conserved, so that doesn't change. So it comes down to estimating the middle term. All right, so how do you estimate the middle term? Well, I think I stopped. All right, so what does he do? So this is the middle term without the norm on it yet. She split it into ultimately many terms. In the beginning, he split it into three parts: a near field, a far field, and a middle field part. All right? And this R is a parameter which you ultimately, at the end, when you're right before applying Gromwalds, you're going to set to a value. And that value will be a function of the v, the function v. All right? I'm not going to go through the details of that, but notice how if v, which measures the L infinity norm of the gradient of u, if that gets larger, then R gets smaller, exponentially fast. So think of this R as a very small number. So it turns out you can estimate the near field and the middle field, the far field and the medium field very easily. I won't bore you with that estimate. And it comes down to dealing with, it comes down to dealing with then just the one term right here. Okay? Of course, I didn't include the integrand in that term. And that term we're going to rewrite, because things are smooth, you can rewrite it in terms of a cutoff function. So this cutoff function is a scaled version of A. A looks like this. This is the absolute value of x is A of the length of x, and that's the length, then that's A times the length of x. So A sub r, since h is going to 0, h minus will be less than r, is going to, this mu of rh is going to look like this. That's 2r. Okay. Didn't draw that so well. That's 1, and that's 2. Right? So mu of rh is that kind of a cutoff function. And so it remains to estimate that integral. So how does he estimate that integral? Splits it into a total of, 12 different parts, something like that. Okay? Lots of different pieces. And almost all the pieces are pretty easy to estimate, using just basic estimates in the BOS of our kernel. But the hard to estimate part, which is perhaps not surprising, is when you have still the full gradient of the BOS of our kernel. So it's cut off, but it's cut off only partly. So the mu r has been taken from being on the outside. Ideally, you bring it all the way inside next to the g. You can't do that. So it's in between. So how do you estimate this thing? Well, you can't use Young's convolution inequality because all you really have is omega is an L infinity, and that piece, gradient of mu RH, gradient G, is not uniformly in L1. Okay? You can trust me on that. It just isn't. So what do you do? So this is where he brings in this crazy-seeming lemma. All right? So we have a 2x2 matrix M. Has to be invertible. Then if you want to, so this comes out of the blue. The M's brought out of the blue. You're trying to estimate B, but M you just make up. So how do you make up M? Well, you make it up in such a way that that estimate works. So is useful. So what does it mean for the estimate to be useful? Well, first of all, in the estimate trace of B has to be estimable. So if B doesn't have a good trace to begin with, then forget it. So that's a one requirement of B right up front. You have to be able to find a column vector M1, so the M1's easier to estimate than B is, which is a big challenge. And then you have to find a second column for M, which just has to be there to keep the determinant of M from being 0. Okay? If you can do all that, then you've got your estimate. Okay? Does this ring a bell to anyone where this thing, does this look familiar at all in any way? It's very strange looking. The a to the fifth plus b to the fifth plus c to the fifth plus d to the fifth. Serfati just says it's some polynomial of degree 5, but that turns out to be what it is. Okay. Well, good. We should have been mystified then. All right, so what do you do? Well, it turns out the m that works is quite simple. So the expression looks a little bit weird, but the first column there is y, and y is the push forward of y naught. The second column is the push forward of y naught perp. So he's pushing forward both of those things and making the first column y and the second column the push forward of y naught perp. So a computation gives that expression for the determinant of m, but the determinant of gradient in the flow map is 1 because it's incompressible. And and you get that y naught by assumption is bigger than or equal to c on a set on the set sigma delta, which was the closed set where your discontinuities were in a distance delta away from it. And so if you have the cutoff function, which maybe I didn't describe that cutoff function yet, I can't remember. Chi is a cutoff function on sigma delta, okay, if I haven't said that already. So the determinant of m part's easy. That's bounded away from 0. Okay, and then I'm going to write b. B was, where was b? B was right there, it's third line from the bottom. So writing that out in components, b is this. So the trace of it, just add the pieces together. We'll apply the product rule, then add the pieces together, and you get an Laplacian of g. But you got cut off, so that goes away because the Laplacian of g is delta function. And you have only the first two terms. Okay? But each of those is bounded very simply in the manner. Well, I'm running out of time, so I won't go into any details there. But the point is, the gradient of this function is 0 here and it's 0 out here. Okay? And in fact, I drew this a little bit wrong. Right? It really goes up. No, that's fine. That's fine. I drew it correctly. So the gradient is 0 only in those intervals, and then you get an estimate, a very simple estimate on the trace of b. Right? That's not the hard part. B is the hard part. So what is b? I just copied down b again. So b times m1 is b times the vector y. Just multiply them out together, and you get a sum of two pieces. Okay? All right, so what do you do with those pieces? They look pretty ugly. So what you do is you subtract and add. So this piece right here is just this one and this one. D sub k meaning 1 or 2 for L1 and L2. D1, D2 corresponds to L1 and L2. Right? And this is just that expression. Subtract this thing and then add it back in. When you add it back in, you get a divergence. If you get a divergence, you have some hope, because things that are divergence, form of divergence, tend to be transported. Right? And the other piece will estimate in a minute, as we'll see in a minute. Okay? So, you don't have to follow all the algebra here. It's just, the point is to get to where you can write this thing as the D's and the E's. All right, so then we use a little lemma. And I should say, actually, this is not, as I'll say in a minute, the way Serfati does it, because when he has the approximating sequence, he has a remainder term he has to deal with at this point. And there's another way to do it, which is a little more elementary, actually. But it's harder to explain because they need to define things. So we're going to treat this as you would treat it if you didn't have that remainder term. Right? All right, so use a little bit of a lemma, and that says if you've got this cutoff function up here within your BO sub r kernel, because grad g is basically BO sub r kernel, and you're convolving basically, well, it's not really quite convolving, but it's x minus y, and then you're taking f of x minus f of y. Then you can bound that by a constant times the C alpha norm. Well, it's a homogeneous norm, but it's hence by the C alpha norm, and the L infinity norm of G, and then the R, which is involved in your cutoff, raised to the alpha. And remember, R is ultimately set to that value, which is going to work to close the estimates for the Grand walls. All right? And then the second estimate is somewhat similar, but there's no difference between the two of them. Okay? And you're estimating in the C alpha minus 1 norm. So the proof of it is to simply is very simple. You just change variables, so rho is x minus y, and then and then you bound the gradient of that's bounded by a constant over rho squared. If you just think about the scaling of the kernel, and you have the difference between f of f f of x and f of y is bounded by the C alpha norm, and you integrate that thing, and that's exactly what you get. And for the second lemma, what you do is you use a definition of the C alpha minus 1 norm as being derivatives, basically, of things in C alpha, and you force an integration by parts. And you have to give up a little bit of factor because there's an infimum in the definition of the C alpha minus 1 norm. Okay? But whatever. So the idea is you use these two lemmas for those two different pieces. And so for the lemma, for the first piece, going back to what dk was, so I've just plugged in what dk is and took the absolute value, and then wrote it as a convolution. So that's where you kind of see what's going on. This is what Serfati does a lot. It's what, is you force something that is you take a convolution and force something that looks like the convolution, except one of the things is outside instead of inside the convolution, and then you get the difference where that lemma or lemma similar to it apply, and you turn the crank and you get a bound, which now brings in the C alpha norm of y. And then to close it, the C alpha norm of y is ultimately going to be a bound in terms of an integral of the gradient of t, L infinity norm of the gradient of u, rather, as we'll see. And note that's independent of h. Okay, and then for the ek, you use the second lemma, and then in this case, you're going to apply something that's proved in Chemin's paper, which gives a bound C alpha minus 1 norm of the divergence of omega y. But it turns out you don't actually have to use that lemma. Right? In some sense, it's easier, but that lemma uses paradifferential calculus to prove it, which, kind of would like to avoid. Right? All right, so that's the idea of bounding that term. All right, so then there's further estimates. I'll talk a little bit about them. But the idea then is, that you end up closing. This is what I said before. All right, so you bound the V of t in terms of the C alpha norms of y and the C alpha minus 1 norm of the divergence of omega y, and then you bound this and this in terms of the integral from 0 to t of v of t. I said in terms of v of t, it's supposed to be an integral in time, and then you can end up closing things using Grunwalds. Right? Okay, fine. So how do you estimate y? We estimate y in two ways, in L infinity and C alpha. Estimating in L infinity is very simple. That's a standard. Go to the flow map by the L infinity norm, and you'll get the estimates on the bottom. Okay, this last estimate only applies on the support because you have to stay, of chi's, you have to stay near your sigma, where you have a lower bound and y naught. And then to estimate in C alpha, is slightly more complicated. We bring in the C alpha norm. And to do that, we then need an estimate right here. And this is a key estimate. So in Bertozzi and Constantine's paper, that's estimating the gradient of u times grad perp phi. Okay? And then to estimate the gradient of eta, that's just a standard estimate in terms of the integral of the gradient of u. Okay, L infinity norm of the gradient of u, which is bounded by v. So 2 is easily bounded this way. Right? So it comes down to 1. How do you bound 1? So to bound 1, well, you can use literally a lemma, which comes from, which is in Bertozzi and Constantine's paper, and say, I should say, wait a minute before I do that. No, that's fine. So before, when we were bounding the one term, we had the gradient of mu r h times the gradient of g. So that gradient of g might as well have been a k. Okay, so it's really grad perp of it. And so now we have the gradient of k without a cutoff. Before, we used a very elementary bound because we were only integrating up to 2r because of the cutoff function. Now we don't have that. Now we can't get away with that. But that's okay because this is exactly the kind of term that we need. All right, so if you use the lemma of Bertozzi and Constantine, which uses a fairly high-powered result of Kotler's, then you can get the bound. The highlighted inequality is not part of the lemma. It's the conclusion of the lemma, but I couldn't fit it in the slide otherwise. So you use the intermediate inequality, and gradient of k star omega is part of grad u. Okay, and in fact, it's less than or equal to v of t. And so, actually, I don't even need to add the L infinity norm of omega there. I just need v of t. Okay. And so that's the thing you need to close. So you're at this point, it's easy, with this lemma, it's easy to close it. Okay, but actually what Serfati does is he uses another lemma, which is equivalent in the special case of the Biot-Savart law, but it's a very elementary proof which he gives. Okay? So again, avoids any sort of hardcore analysis. And he actually does give the proof of that thing. All right, so the matrix A. How much time do I have? 10 minutes. 10 minutes? Okay, good. All right, so then, right, 10 minutes. That should be enough. So what we're trying to do with A is find some A that's smooth, well, C alpha smooth, which cancels out the singularity and the gradient of U if you combine it with the singularity that's in omega. So this doesn't say anything about the smoothness of omega. It says something about the smoothness of gradient U after you sort of compare it to omega, if you will. Right? And in the very last sentence of his paper, he states an A and gives a cryptic sort of proof, literally the last sentence, which is terse even by his standards. And he states this value of A, which we can't even understand what it means and figure it out. But in any case, after trying to figure it out, we sort of understood, I think, what he was trying to do. And what it turns out to be is, as far as we can tell so far, so work in progress, is what you really have is the first part of the expression for the gradient of U. If you recall, the gradient of U for the smooth solutions, right, was omega over 2 times 0 minus 1, 1, 0, plus, well, it's really the principal value of, well, I'm going to write it that way, the principal value of the integral of the gradient of K of x minus y times omega y dy. So what you really do is you subtract off this multiplied by omega. But, of course, you have to stay within the point at which you have control, so you need the cutoff function chi. Right? So why is this true? Well, of course, you're using a sequence of smooth solutions because this expression isn't going to work in the limit. Okay? Although you can make something if you bring in a Riesz transform in the limit, but it's not going to work in the limit. So you have to work with the approximate sequence. But again, I'm going to suppress that fact. Right? And it means the following proposition, that in fact the principal value part over here, okay, on the part, as long as you have that y vector field to control things, is in C alpha. So you have to multiply by y squared. Of course, y can vanish outside of sigma delta, so you lose control outside of there. Okay, but within the sigma delta region, you actually get this control. And then the result would follow from that because of the expression that I have up there, which I copied down here. No, omega is not C alpha. But you notice we're subtracting this part off. We're getting rid of this. And then it turns out that this part is C alpha in the limit. Yes. That's why. Oh, no. Not using it. No. That's the weird thing. All right, so to deal with, okay, then you have to piece it together with another vector field to get it in the whole space, but let's not worry about that. All right, so let's look very quickly, because I am running out of time, at the idea of what the proof is. The idea of the proof is to inject by force the y into that expression right here, which has no y. Okay? And this y is going to combine with omega in a way that allows you to have the divergence of omega y, which is smooth. Okay? Which is pretty much a wild thing. And this is not what Serfati does. We don't know what Serfati was doing. Okay? It's just something that we did. So if you do a calculation, pretty brute force calculation, you get this matrix A, B, B minus A, where A and B are given as in expressions right there. Okay? But you notice, even though this isn't seemingly what Serfati was doing, his original expression he wrote down in the middle of the page has that same smell. So he probably was thinking this, but it's very unclear from what he wrote. Right? So fine, what we need to deal with are things of the form gradient K1, tilde star omega, where tilde star up here is a convolution, but the principal value. Okay? So, yeah, right. Which I guess in some sense you could view as a convolution. But so then what you do, and I'm not going to give the details because I'm running out of time, but you're doing essentially the same thing that we did before. You subtract and add in order to force the divergence to get in there, and use the same two lemmas we had before to control what's going on. Okay? So here we write this as this subtracted and then added. This is going to come into a divergence because that's, after integrating by parts. And this part we're going to bound using the same lemma as before. Okay, so first part bound as we did before. And then it remains to bound the second term. And to bound the second term, we prove that this holds true, which requires some smoothness of omega. It requires smoothness of omega, not in the limit, only in the approximating sequence. Because the way you integrate by parts here is it's a principal value. So you integrate over a ball. And you need to show that the boundary term vanishes on the ball. And it will vanish on the ball given y's and C alpha and omega is smooth. And it is in the approximating sequence. This fails in the limiting solution. This wouldn't work. So you have to do it all with the approximating sequence. Well, I know I'm going a little too fast to make that clear. Okay. All right. So in the remaining time I have, I talk about 5 minutes left, something like that. More? Oh, so too much time. All right. So some directions you might be able to take Serfati's approach. And I mentioned, I think, all three of these in the beginning. Bounded domains, vortex-wave system, which I'll explain, and these bounded vorticity, bounded velocity solutions to the Euler equations. All right, so let's look at a little bit of what's going on in the bounded domain. Let's just consider it a disk. So in a disk, the Biot-Savart kernel can be written down very explicitly as a difference between k of x minus y, k being the Biot-Savart kernel as before, and k of x minus y star, while y star is reflection across a disk. So k of x minus y is the same as in the whole space, and all the key estimates are going to apply that applied for Serfati. But k of x minus y star has a problem. But it only has a problem when you're on the boundary, because it's perfectly smooth when you're away from the boundary. So the vortex patch starts away from the boundary. You've got no problem at all. Okay? And so there's almost nothing to do. But if it does hit the boundary, then things become interesting. Because k of x minus y star itself isn't too bad. It blows up no faster than k of x minus y. But the gradient of it in y, which enters in when you integrate by parts, which you have to, that baby's hard to control. Okay? You can control it in the far field, but controlling the near field is difficult. And so there's something interesting to go on here. And DePaul, in his paper from 1999, who's kind of adapting Chemin's approach, gives a result if you're away from the boundary for a global in time, but gives a short-time result when you're up to the boundary. And it's not clear that we can reproduce that. But nonetheless, it's just something we're starting to think about. All right, so bounded vorticity, bounded velocity. These are solutions which I guess Helena and Milton and David Ambrose and I have been working on lately. And we call them Serfati solutions in honor of Serfati. And the idea here is you have no decay of the vorticity, and so you cannot apply the Biot-Savart law. But there is a so-called Serfati identity, which says that the velocity at time t can be written as a velocity at time 0, if you move that to the right-hand side, plus something that's like the Biot-Savart law. A is a cutoff function, radial cutoff function, like as before. And then a remainder term, which is the far field effect, so to speak, from the Biot-Savart law. And here, star dot, maybe I defined before. No, for a matrix is just convolve each component atom together. So it's a nice terse way of writing this. Okay? And you notice the second term, C infinity, because this grad k is like 1 over C over x, C over the distance cubed. And U tensor U is in L2. So really you can apply all the derivatives you want to that. So it comes down to the first term. Okay? And what can you do with the first term? Okay? So the first term itself can be bounded. It can be handled like Serfati, because that cutoff function really doesn't hurt you. So those parts of Serfati's proof go through okay. So it's likely that it works. Okay? But one difficulty which comes up immediately is this equivalence between k star, the divergence of z being in C alpha, and divergence of z being in C alpha minus 1, which even though he doesn't use the equivalence literally is key to the stuff he's doing, is going to show up and is going to be a problem. Right? And also, this kind of thing should also work in an exterior domain, since we work the Serfati's solutions out in an exterior domain. At least it should work as well as in a bounded domain. Okay? All right, and then finally, there's this vortex-wave system. Vortex-wave system, which I've written here, what it's saying is basically there's a point vortex which is moving according to this differential equation, ODE, z dot of t equals the velocity at time t and position z. But the velocity is coming from a vorticity, which is sort of a background vorticity. And that background vorticity solves the Euler equations, except that the velocity for the point vortex is included in the Euler equations. Okay? So it's sort of a coupled system. So it's u plus h instead of just u there. And the whole thing evolves along. Okay? So z is the center of the vortex, and h is the Biot-Savart kernel, k, translated by z. So what's known about this, well, I suppose a number of things are known about this, but the two significant things for what I want to say are first back in 91 on Marchioro, yes, and I won't say it again, and Polverenti proved the existence of solutions for Serfati initial data, okay, and existence without uniqueness. And in this case, you get a log Lipschitz velocity field, which is pretty cool, and z is in C1. Which is a pretty good level of regularity to have. And it wasn't, and there was an intermediate result before them in Lecoq and Millau, but Lecoq and Millau in 2009 proved that if the initial vorticity is constant near the vortex, then in fact you get uniqueness. Okay? If you don't have that, uniqueness is open. The idea being that the point vortex can really churn things up really near, because it blows up like 1 over r. Okay, so it can really churn the vorticity up, and the smoothness could be lost right away. Okay, so if you consider vortex patch data where you put the vortex right in the middle of the vortex patch, where you have constant initial vorticity near the vortex, and so, of course, you get uniqueness. And pretty much everything that Serfati has goes through with almost no change. Okay, and that would be true of either of any three of the approaches, Chemin's approach or Bertozzi and Constantine's approach. So that, those estimates should go through fine, and I think that would be a fairly simple result. More interesting would be to ask the question, can you say anything in the situation where you have a non-unique solution, but you have a solution that's reasonably well behaved? Is there anything you can say if you don't have constancy near the point vortex? All right? And so that, and so one of the reasons you might expect you can say something is you should expect it away from the point vortex that if you're C alpha, then you're going to remain C alpha as long as you start in a region that's bounded away from the vortex. Because the estimates for the propagation of regularity of the flow map and of smoothness and vorticity ought to go through, and I think do go through if you stay away from the point vortex. Right? And so there's some chance you can say something about this in that setting, though I'm far from certain of that. All right, so in conclusion, I would just say that Serfati's proof, it's very short. It's really an announcement more than a research paper, I guess. It's extremely terse, and it's really hard to tell what he's doing. And a lot of times you just have to use it as inspiration for what maybe he's thinking, and then just do it yourself, right? Yeah, and then his definition of AATs may be a little bit suspect, but nonetheless, it's an elementary proof, and it's a pretty flexible one, and I think it was worth our effort to try to understand it, and we're still at least a few months away from having a preprint, but I think hopefully the effort turns out to truly have been worth it. So, thank you.
Questions for Jim?